Hey everybody. So today we're going to take a look at double angle identities. You'll remember that yesterday we did sum and difference identities. That was lesson 7. Today is lesson 8, which is actually the second last lesson in our trig equations and identity lesson. So we're almost there. Good job. So right before we start here, this is not in your notes, but what I'd like to do is just this quick little review question. It says if the point 2, 5 lies on the terminal arm of angle x in standard position, what's the value of cos of pi plus x? Now, I want you to see cos of pi plus x, and I want that to be recognizable to you. Cos of pi plus x is in the format of cos of a plus b. So if you look at your handy-dandy formula sheet, you know that cos of a plus b is cos of a cos of b minus sine of a sine of b. Now, remember yesterday, I talked about making sure you realize who's A and who's B. So for this guy, A is our pi and B is our x. So if I just translate that into the context of the question that I'm currently in, it would look like cos of pi cos of x minus sine of pi sine of x. Now, I have to figure out a little bit about x. So that's where I'm going to look at the angle that I have. Remember that this point would represent an angle, or this point would represent a point that's on the terminal arm of an angle in standard position. So I know I'm in quadrant 1 because I have the point 2, 5. So I draw my angle in standard position. I know that my x value is 2 and my y value is 5. That's enough to use the Pythagorean theorem. 2 squared is 4, 5 squared is 25. Add those together, I get 29. So I know my hypotenuse is the root of 29. Now, that allows me to now say what the cos of x is. The cos of x as a ratio would have to be 2 over root 29, and the sine of x as a ratio would have to be 5 over root 29. Now, pi, we already know, so the cos of pi is -1, so I've also filled that in, and the sine of pi is 0. So it was kind of a moot point to say that the sine of x was 5 over root 29, but I wanted to have the discussion anyway. Yes, it does get multiplied by 0 there, so this whole section is actually gone now, and we're just left with -1 times 2 over root 29, and so the cos of pi plus x would end up being -2 root 29 all over 29. So I multiplied that, and then I also rationalized it. I just multiplied it by root 29 over root 29, so I didn't have a radical on the bottom. Saying -2 over root 29 would have been perfectly okay as well, as long as the question did not say state your answer in rationalized form. Okay, so now I'm in your book now where it says double angle identities. We're going to start right there, and what we're going to do is just quickly derive them because these are easy derivations. They come actually just from what we did yesterday. So for sine of a plus b, we knew from yesterday's lesson that sine of a plus b is sine of a cos of b plus cos of a sine of b. What would happen if we let a equal b? Essentially, if we let a equal b, we're now looking at sine of a plus a, because a and b are the same thing. I could just as easily say b plus b. It doesn't matter. I just chose to replace the b with a if they equal each other. So sine of a plus a gives me sine of 2a, which is what we call a double identity. It's 2 times the angle a. But if I do that to this guy, I'm also looking at sine of a, cos of a, and sine of a. So that gives me this. Now, sine of a, cos of a is the same as cos of a, sine of a, because the order of multiplication doesn't matter. And so that ends up being 2 sine of a, cos of a. So that's the sine of 2a. Now we're going to do the same thing for cos. So if I'm looking at cos of a plus b and I let a equal b, then that means I'm now looking at cos of a plus a, and that's going to give me cos of a minus sine of a sine of a. Well, cos of a, anything times itself is just that thing squared. So that'll be cos squared of a, and this will be sine squared of a. So I end up with cos of 2a equals cos squared a minus sine squared a. Now, with the cos of 2a, there are 2 more derivations I can make, and we get those from just taking either the cos squared a or the sine squared a and manipulating those with our Pythagorean identity. So we know that the cos squared A is the same as 1 minus 2 sine squared A. So if I did that replacement over here, I just replaced my cos squared A with 1 minus sine squared A. And sorry, I think I said 2 sine squared A there. 1 minus sine squared A was the replacement. I was getting a little ahead of myself. As you can see, the answer is going to be 1 minus 2 sine squared A, because I end up with a negative sine squared A and a negative sine squared A. So just for clarification, this one came from me taking this cos squared and replacing cos squared with the Pythagorean identity. Cos squared A is the same as 1 minus sine squared A. Okay, and then that gives us for cos 2A another identity that we can use, another derivation that we can use, which is 1 minus 2 sine squared A. Now, likewise, I could go back to my original, which is cos squared A minus sine squared A, and I could replace my sine squared A with 1 minus cos squared A. Now, when you do that one, you have to be a little bit more careful with that derivation, because anytime you're doing a substitution where it's subtracting, that subtraction sign has to follow through to every term that is involved in the substitution. So essentially it has to be in brackets. So we end up with cos 2A equals cos squared A minus, and then here's my substitution. The sine squared A is 1 minus cos squared A. Now, that negative, as I just said, distributes to both of those terms. So I end up with a negative 1 here, but this is a plus cos squared A. So cos squared A and cos squared A give me 2 cos squared A, and then the minus 1. So there are three double angle identities for cos, and they are this green one here, this pink one, and this orange one. Okay, then we also have tan. Same setup to do the tan double angle. We take the sum one, which is tan of A plus B is tan of A plus tan of B all over 1 minus tan of A tan of B. We're going to replace A with B or B with A. We're going to say that A and B are the same thing. So every time I see a B, I'm going to replace it with A. So that's going to be tan of A plus tan of A all over 1 minus tan of A tan of A. Now, tan of A plus tan of A, this top part here, that ends up being 2 tan of A. And then tan of A times tan of A, this bottom part, that ends up being tan squared A. So tan of 2A equals 2 tan of A minus, 2 tan of A divided by 1 minus tan squared A. Now, that can feel a little overwhelming. If you're sitting here trying to copy all of this down and thinking, how am I ever going to memorize all this? You don't have to. All of these are on your formula sheet. So what I've just done with you is I've taken you, yesterday we did from all the addition and subtraction ones. So now we had 2, 4, 5 left to talk about. The bottom 5 there are all double angle identities. So that is all the last 5 identities that you have to deal with. Okay, so they're all on your formula sheet. You do not have to memorize them. You just have to understand how to work with them. The trick to all identities, practice, practice, practice. So what we're going to do with this lesson is we're going to go through a few proofs, and then we're going to go through a few examples of other types of questions we can ask you with the double angle identities. Okay, so the first question here, prove the following and state any restrictions. So we've got 2 tan x all over 1 plus tan squared x equals sine of 2x. Now, if we're talking about restrictions, the first thing you may want to look at is you may want to say, okay, hey, this whole bottom can't be 0. Well, that's an interesting conversation. If I set that bottom equal to 0, I'm going to get tan squared x can't be negative 1 because I just brought my 1 over. And at this stage, I'd have to square root it. I can't square root negative 1, so there are no restrictions involved here. But I do see a tan on the top and on the bottom. So tan, the fact that tan is on the bottom, remember that tan of x is sine of x over cos of x. So we know that cos of x can't be 0. If cos of x was 0, that tan would be undefined. So we know for sure that cos of x can't be 0. Now, can sine of x be 0? Well, it actually can in this one because it's 1 plus tan squared there. So even if sine of x was 0, that would make this whole thing 0, but I wouldn't end up with a 0 on the bottom of the fraction because I'd end up with 1 plus 0, and 1 plus 0 is totally okay. So it's just that cos of x can't be 0 here. So then we think about my unit circle, Calgary Stampede. When is cos of x 0? When is the x value 0? That's at pi over 2 and 3 pi over 2. Okay, so we're going to say theta can't be, or x can't be in this example, sorry. X can't be pi over 2 plus pi n, where n is a member of the integers. Okay, pi over 2 plus pi n, where n is a member of the integers. Awesome. So now, how am I going to solve this? Remember, I got to work on the left side, I got to work on the right side, do it simultaneously, just never cross sides. So I see the sine of 2x, and I'm thinking, okay, sine of 2x, I know right off the bat, that's right on my formula sheet. For the most part, you never want to deal with a double angle. You always want to try and get rid of the double angle, okay? So I'm going to change my sine 2x to be 2 sine x cos x. And then I'm going to go over here and I'm going to say, okay, what can I do to that other side? So I see 2 tan of x over 1 plus tan squared x. Now, what I'm going to do is there's a couple things I did here, but they didn't affect each other. That's why I'm allowed to do a couple things all at once. First of all, I said, okay, tan is going to be sine over cos, so that 2 tan x that you see on the top here, I'm just calling 2 sine x over cos x, okay? And then I wrote it as a division statement, so I'm saying divided by, and then if you look at your formula sheet, 1 plus tan squared theta is actually a Pythagorean identity. 1 plus tan squared theta is secant squared theta. So I changed my 1 plus tan squared theta to secant squared theta. Now, secant squared theta is 1 over cos, so I changed my secant squared theta to 1 over cos squared theta. Now I'm dividing fractions, so I'll multiply by the reciprocal. One of these cos x's will divide each other out, and that will leave me with 2 sine x cos x, which is exactly what I had over here, 2 sine x cos x. So left side equals the right side, and this proof is all done. Okay, awesome. Next guy is sine theta plus cos theta all squared equals 1 plus sine 2 theta. Now, again, first thing you want to think about is restrictions. There is no restrictions in this one. So I've actually physically written no restrictions. You don't have to write that. It's just for the purpose of this note, I want to make sure that the very first thing you think about is always restrictions. So if it's going to help you to write no restrictions there, to remind yourself that you've done that check and that there is for sure no restrictions, then go ahead and write that. If I was marking this, so I'm not looking for you to physically say no restrictions. Okay, so again, we might want to deal with this double angle here, the sine of 2 theta, and just get rid of it right away. The sine of 2 theta is 2 sine of theta cos of theta. Again, that just comes right off my formula sheet. I'm not doing any thought there. I'm just doing a straight up replacement. Over here, that's going to end up being sine of theta plus cos of theta times sine of theta plus cos of theta. So you end up having to FOIL that. Or if you remember to square a binomial, you could square the first, double the product, square the last. If you don't remember that, sine of theta plus cos of theta times sine of theta plus cos of theta, we're going to get sine squared theta, we're going to get sine theta cos theta, we're going to get sine theta cos theta, and we're going to get cos squared theta, okay? So that ends up being sine squared theta plus 2 sine theta cos theta plus cos squared theta. Now, I'm hoping at this stage of the game, you can see this, and your heart goes pitter-patter because you know that sine squared theta plus cos squared theta is 1. So we can go right to calling that a 1, and we're done. We now have the left side equaling the right side, and everything is good. Okay? All right. Okay, so the next question to look at is 2 over 1 plus cos 2 theta equals secant squared of theta. Now, if we were to look at the secant squared theta, right away you can tell me that cos of theta can't be 0. If you think about your unit circle again, go right back to that Calgary Stampede. Where is your x value 0? We're at pi over 2, 3 pi over 2. Now you might want to have a thought about the 1 plus cos of 2 theta. Well, let's just have that thought really quick. That means that cos of 2 theta can't be -1. Okay, now where is cos of 2 theta? -1. Where is the x value, -1? Well, that's actually here. So we're saying 2 theta can't be pi, which means theta can't be pi over 2. And we've already taken care of that right here with that pi over 2. So my restrictions on this guy are that theta can't be, theta can't be pi over 2 plus pi n. Now, what am I going to do with this? Well, remember I said earlier, we always want to get rid of cos of 2 pi. You never want to deal with a double angle. So I have 3 options. Go to your formula sheet. You have 3 options. Doesn't matter which option you choose, except one of them is usually going to get you there quicker than the other guy. So if you look at these 3 options, can you see one that might be a little more friendly? The one I want you to notice is that 2 cos squared theta minus 1, because you've already got a plus 1 here, so that'll help your 1's go away. So the first thing I did was I took my secant squared theta, changed it to 1 over cos squared theta. Now I'm going to take my cos of 2 theta and change that to 2 cos squared theta minus 1. My 1 minus 1 is gone. And then my 2 over 2 would reduce to 1, which leaves me with 1 over cos squared theta. Left side equals the right side. Okay. All right. So that's it for some proofs. Now we're going to just go through a couple other types of questions that we could ask you that involve double angles. Okay, so give the exact value of 1 minus 2 sine squared of 22.5 degrees. Before you get going on this one, I need you to see that that says 1 minus 2 sine squared of something. You go to your formula sheet and you say, hey, can I see 1 minus 2 sine squared of something? Yes, cos of 2 theta is 1 minus 2 sine squared theta. So this is cos of 2 times 22.5, because theta here, or alpha on your formula sheet, is 22.5. So I'm saying 1 minus 2 sine squared x is the same as saying cos of 2x. Therefore, I know that this is now going to be cos of 2 times 22.5. Well, 2 times 22.5 is 45, so this just becomes the cos of 45, which is root 2 over 2. Okay, next guy. If tan of theta is 5 over 12, and theta is somewhere between 180 and 360, determine the exact value of, and the first one is cos of 2 theta. Okay, so a couple of things I need you to see here. If I'm between 180 and 360, I have to be in quadrant 3 or 4. Tan is completely positive, which means I have to be in quadrant 3, because if you think about the CAST rule, tan is only positive in quadrant 3 when comparing quadrant 3 and 4 together. So I need to think about the fact that I'm in quadrant 3, so I've drawn an angle in standard position in quadrant 3. Tan is the opposite over the adjacent. Be real careful here. You have to remember that this has to be the -5 and -12 because of the quadrant that I'm in. Then I'll Pythag my way to the hypotenuse. 12 squared is 144, 5 squared is 25. That gives me 169, and the square root of 169 is 13. Okay, so now I know 13. So now I'm heading to cos of 2 theta. I have 3 different options for how I handle that. It doesn't really matter which one I choose. I happen to have chosen here 2 cos squared theta minus 1. I now know that cos of theta, remember, now that I have this triangle, cos is adjacent over hypotenuse. So I'm looking at negative 12 over 13. So I'm looking at 2 times negative 12 over 13 squared minus 1. Squaring a negative gives me a positive. So this guy here is going to be 144 over 169. Then I'll multiply that by 2. So that ends up being 288. And then I subtract 1. Now, if you're trying to do that in your head, 1, you're just going to call that 169 over 169. So you're looking at 288 minus 169. Or if you want to use a calculator, that's fine too. You should end up with 119 over 169. Okay, 119 over 169. Now, if this was on a test and you wanted to check your work to make sure you're right, you have the power to do that. You could arc tan 5 over 12, get a reference angle, figure out what your angle is in the third quadrant based on that reference angle, and then go cos of 2 times whatever that angle is, and you should get 119 over 169, okay? But this would be the work that we'd be looking for if we asked you a question like this on a test. Then we asked you for the sine of 2 theta. Now there's only one option for the sine of 2 theta. Sine of 2 theta is 2 sine of theta cos of theta. And now looking again at this diagram, we know that the sine of theta is negative 5 over 13 and the cos of theta is negative 12 over 13. So now I just multiply all that together and I end up with 120 over 169. Okay. All right. Multiple choice question. The expression 1 plus cos of 2 theta over sine of 2 theta, where theta can't be n pi over 2 and n as a member of the integers, is equivalent to which? So again, we're just going to take this and we're going to start working with it. Sine of 2 theta, I don't have any options for that, but changing it to 2 sine of theta cos of theta. Cos of 2 theta, I do have options. Again, I probably want to try and get rid of that 1. So if I had one that said a negative 1, that would probably be the one I'd want to try. And of course I do. So I'm going to change my cos of 2 theta to 2 cos squared theta minus 1. And I'm going to change my sine of 2 theta to 2 sine theta cos theta. Now, 1 minus 1, that's gone. 2's are going to go. Now, just be careful with this. The 2's divide each other out because 1 minus 1 is 0 and there's just one term up there. If there were several terms up here, those 2's wouldn't divide each other out, but the 1 minus 1 makes those 1's disappear. That would leave me with 2 cos squared theta over 2 sine theta cos theta. So at that point, my 2's will divide each other out and 1 cos would divide each other out. So that's going to end up leaving me with cos theta over sine theta, and cos theta over sine theta is cotangent theta. So the answer has to be A. Awesome. Okay, now we'll take a look at this guy. Point A, which is x comma y, is the intersection point of the unit circle and the terminal arm of 145 degrees in standard position. The coordinates of point A to the nearest hundredth are. This becomes a super easy question if you go back to our lesson on the unit circle and you remember that every point on the unit circle, remember what I keep writing here, every point on the unit circle is Calgary Stampede. It's the cos of that angle, comma, the sine of that angle. So when you're asked for this point, you literally just have to go cos of 145, that's the x coordinate of that point, sine of 145, that's the y coordinate of that point. And so when I do that, I end up with negative 0.82, comma, 0.57. Okay, given a point on the unit circle is 0.56, comma, 0.83, determine the value of sine of 2 theta, round your answer to the nearest hundredth. Okay, so a few things we have to do here. First thing that I want you to think about, just same conversation that I had on the previous slide. If I know that this is a point on the unit circle, I know the cos of theta is 0.56, and I know the sine of theta is 0.83. So if I expand sine of 2 theta, I know that sine of 2 theta is 2 sine of theta cos of theta. Well, I already know what the sine of theta is. I already know what the cos of theta is. I just plug those values in and multiply. That's going to give me the sine of 2 theta is 0.9296. Then I was asked to round to the nearest hundredth, so sine of theta is 0.93. The last example, again, very similar. There's just a little extra work here because we're going to have to, in a minute, solve for k. But given a point on the unit circle is 2k, comma, negative 3k, determine the value for cos of 2 theta. Now, the way I decided to set this up is let's first just deal with the fact that this guy represents cos of theta, this guy represents sine of theta, just like I did on the previous slide. So I said it doesn't really matter which one I chose, but I chose cos of 2 theta is cos squared theta minus sine squared theta. I plug those values in, and I end up getting cos of 2 theta equals negative 5k squared. Okay, so all I've done is I knew cos of theta was 2k, I knew sine of theta was negative 3k, I squared them both and then subtracted them. Okay, but it says what's the value, so I need to figure out what k is. If I can figure out what k is, then I can just plug in my value for k, and then I have an actual value for cos of 2 theta. Well, how do I figure out what k is? Again, remember that you are on the unit circle. So if you're on the unit circle, this has to fit in the equation of the unit circle, which is x squared plus y squared equals 1. So that becomes an equation that I can actually use to solve for k. So x squared plus y squared equals 1. That's going to give me 4k squared and 9k squared. And so k ends up being, I'm going to divide both sides by 13 and square root. K ends up being plus or minus the square root of 1 over root 13. So now that I know that, I can say, okay, let's go plug that in for k here and actually figure out the value of cos of 2 theta. If I plug that in for k, I ignored the fact that it was plus or minus because I'm going to square it anyway. So when I square it anyway, I'm going to get a positive answer. And so that's going to give me 5 over 13. Negative 5 over 13. This guy's positive, but I'm multiplying it by negative 5. So cos of 2 theta is negative 5 over 13. So that's kind of the fun stuff that we can do with double angles. Your job now is to go through the practice section, and I posted the page numbers there. And then tomorrow what we're going to do is we're going to go back to the whole notion of solving equations, but now the equations that we have will have identities embedded in them. So we have to be able to solve the equations using all of these identities that are on your formula sheet. Okay, awesome. Hope this helps. Make sure you're asking lots of questions as you go through, and make sure you're practicing as much as you can. Have a great day, guys.